Today we're creating a symbolic mathematics library entirely from scratch. It will parse mathematical expressions, simplify them using algebraic rules, compute exact derivatives with respect to a variable, and even evaluate the expressions numerically. This is the kind of engine that powers tools like Mathematica and Wolfram Alpha, and will build it in a single Java class. No external libraries, just pure object-oriented design and a bit of computer algebra. Our first task is to define the atomic units of the math language, tokens. We create an enumeration with types for numbers, variables, the arithmetic operators plus, minus, multiply, divide, and power, and parentheses. There's also an end-of-file token to mark the end of the input. A simple token class pairs a type with an optional string value. For numbers we store the numeric text, for variables we store the name. This is the input vocabulary our parser will consume. The lexer takes a raw string and breaks it into tokens. We first strip all whitespace, then scan character by character. For plus, minus, star, slash, caret, and parentheses we emit the corresponding token immediately. When we encounter a digit or a decimal point, we greedily consume characters to form a number token. For letters, we collect a sequence of letters and digits to form a variable token. Any other character triggers an error. This simple scanner is the bridge between the text and the. We design an abstract expr class that every mathematical node will extend. It declares methods for evaluation, taking a map of variable values, differentiation, with respect to a variable, simplification, returning a new reduced expression, and a prefix notation for debugging. Each concrete subclass will implement these according to its role. This polymorphic design lets us treat complex nested expressions uniformly, just like a real computer algebra system. The simplest nodes are number and various. A number wraps a double value. Its derivative is always 0, its simplification returns itself, and evaluation just returns the number. A var stores a variable name. When differentiating, it becomes 1 if it's the variable we're differentiating with respect to, otherwise 0. Evaluation looks up the variable in the supplied map, throwing an error if it's missing. Both override to string for human-readable output. Add and sub hold left and right sub-expressions. Evaluation sums or subtracts the results of evaluating the children. Differentiation distributes over the operation. The derivative of a sum is the sum of derivatives. Simplification uses algebraic identities. Adding or subtracting 0 returns the other operand, and if both sides are numbers we fold them into a single constant. Their string representations add parentheses to maintain proper precedence. Mul and div follow the same pattern. Multiplication's derivative uses the product rule, derivative of the first times the second, plus the first times derivative of the second. Division uses the quotient rule. Simplification here recognizes 0 and 1, multiplying by gives 0, multiplying by 1 returns the other operand, and similar logic for division. Constant folding combines numeric children. Pow represents exponentiation. Evaluation uses math.pow. Differentiation has two cases. If the exponent is a constant, we apply the simple power rule. If the exponent is variable, we would need logarithmic differentiation. We leave a placeholder that creates a more complex expression involving lane simplification handles the cases of exponent 0, returns 1, exponent 1, returns the base, and constant folding. The neg node represents unary minus. Its derivative is the negative of the derivative O. For the general power rule differentiation, we need the natural logarithm. The ln node wraps an expression and defines its derivative as the derivative of the argument divided by the argument. Evaluation uses math.log. This is a small but crucial piece for handling variable exponents correctly, and it demonstrates how the engine can be extended with new functions. Now we need to turn tokens into our expression tree. The parser class implements a recursive descent parser. It starts with a parse method that calls parseExpr and then verifies we've consumed all tokens. ParseExpr handles addition and subtraction by repeatedly parsing terms and combining them left associatively. ParseTerm does the same for multiplication and division. Unary minus and plus are handled in parseUnary, which optionally consumes a sign and then calls parsePower. Power is right association. To make the library easy to use, we add static methods. ParseExpression takes a string and returns an expr, derivative parses an expression, differentiates it, simplifies the result, and returns the string representation. Evaluate parses an expression and computes its value given a variable map. These functions are the main entry points for users who just want to compute a derivative or plug in numbers. The main method showcases everything we've built. It parses several expressions, a quadratic polynomial, a geometric distance formula, a rational function, a pure power, and a cubed binomial. For each, it prints the original expression, the simplified form, and the derivative with respect to the relevant variable. It also evaluates the quadratic at a specific point. The output demonstrates that the parser works, differentiation rules are correct. And simplification eliminates obvious redundancies. The demo mentions that the logarithm node exists but is not yet fully integrated into the parser, hinting at future extensions. After compiling with javac symbolicmath.java and running it, we see a series of expressions, their derivatives, and the evaluation result. The derivatives of polynomials yield correct answers, the power rule is verified, and the constant folding reduces terms. This validates the core engine. The output is clean and demonstrates the library's capabilities. We've built a fully functional symbolic math engine in pure Java. It understands the grammar of mathematical expressions, builds an abstract syntax tree, performs algebraic simplification, computes exact derivatives, and evaluates numerically. This is the foundation of computer algebra systems. You can now add more functions, integrate. The code is compact yet powerful, showing how object-oriented design and a bit of recursive parsing can handle remarkably complex tasks.